Then let's do brief discussion for Dijkstrata algorithm. First, let's see the complexity of this algorithm. So suppose we have n nodes, and in each iteration, it need to check all nodes which is not in the n prime set. Therefore, in total, we need n times n plus 1 divided by 2. This much of comparisons. So um, since everybody have taken the algorithm class, so you will, after you do a simple calculation, you will know the time complexity for this algorithm is n squared. And probably there are more efficient solutions exist which can implement this problem or to address this problem with n log n algorithm, which is better than n squared. However, the Dijkstrata algorithm will exist some problems. For example, listed here is oscillation problem. Then let's see an example. Suppose here the link cost equals amount of carried traffic. So initially, in this problem or this example, we have four routers. They are connected with each other, and the customers connect with DCB will send a packet all go through or destinated to router A. And the customer from router D and B, they will send 1 unit of data. And the customers connect with the router C, they will send E unit of data. So initially, the topology of the network looks like this. So that means the path finally ended with DA will with 1 unit of cost or one link cost, and the path ended with BA with cost 1 plus E. Then after everybody know this truth or know this status, because Dijkstrata algorithm is depends on the global information, so everybody will know the ground truth of this entire topology. Then router D, C, and B, they will decide to transfer the data through the clockwise path, which will be look like this. Then everybody will transfer the traffic or use the path as a clockwise path or direction. Then we can see the consequence of this phenomenon is the BA will equal to 0, and the DA will be equal to 2 plus E. Then the router D, C, and B, they will do a re-evaluation. They will find, okay, so DA with a higher cost compared with BA. Then everybody will switch their traffic to the counterclockwise path. Then the situation will become like this. So right now, the cost for BA will become 2 plus E, and the DA will become to 0. Then they will change the direction again back to the the clockwise. So if we're using Dijkstrata algorithm, we will facing this kind of a problem. So periodically, everybody or every routers within this topology, they will changing their um, data transfer or data path directions. Then we have finished the link state algorithm. So continually, let's see the distance vector. Distance vector algorithm is based on the Bellman-Ford equation, which is used by dynamic programming. And also we know the distance vector algorithm is rely on the local information. It doesn't like the link state algorithm. The link state algorithm will rely on the global information. Then let's see how the distance vector algorithm works. So we will light this dxy as the cost of least cost path from x to y. Then we will, based on this Bellman-Ford equation, actually this one, to calculate the least cost path from x and to y. So within the equation, so we will looking for the minimum combinations among all the neighbors. So the cxy represent the cost to neighbor v, and this dvy is the cost from neighbor v to destination y. So for all the neighbors, we will check these combinations to see which one can return us the minimum value, and then we just take that router as our next hop. So that's the basic concept of a distance vector algorithm. Then let's see example. So here on the left side, this figure is the topology of the network. So from this network, because it's quite simple, we can directly see the ground truth. For example, the least cost path from V to Z, we can see is a file. This path is from V, X, Y, and Z. For this path, if you add all the costs together, you will get a result 5. And from X to Z is equal to 3, so it's this path, X, Y, and Z. You can see 1 plus 2 equal to 3. And for W to Z, it will use this path, WY and Z. If you add these two paths together, you will get a 3. Then based on the BF equation, you can calculate the least path from U to Z. And we just check all the direct neighbors of U. So first, let's see the cost from U to V, which is equal to 2. We written here. And from V to Z, we already get the ground truth, which is here, equal to 5. Then for this combination, we will get the total cost for this path as equal to 7. And then we check next neighbor. From U to X is equal to 1. And from X to Z, for this path, which is here, equal to 3. So for this combination, we got the total cost is equal to 4. And from U to W is equal to 5. And from W to Z, from this ground truth, we know is equal to 3. So for this combination is equal to 8. So after we calculate the minimum value among these 3 combinations, we get The second one, which is the smallest one, equal to the total cost equal to 4. Therefore, we will know if you want to find the least path from U to Z, the next hop from U will be go to X because it can give us the minimum combination for the entire path. And also for this uh, the node achieving minimum is next hop in shortest path. Therefore, for this X can be added into the forwarding table. If a customer wants to transfer packets from U to Z, it will go through the forwarding table. It will know you will forward this packets to router X because X is using or is on the shortest path from U to Z. Then let's see more details about this distance vector algorithm. So here, since initially we cannot directly to see the ground truth for the least cost path, which is the lowercase d from x to y. Therefore, we need this notation. We call it d capital dy, which is estimate of least cost from x to y. And here, the x maintains the distance vector for dx to every single or every other routers in this topology, this one. And also for the node x, it will know the cost to each neighbor v. That's the part of the local information. So for each router x, it will know the direct link cost. And also node x will maintain its neighbor's distance vectors. For each neighbor v, x will maintain its neighbor's distance vector. If you to this point, if you don't understand the concept or what they are saying here, that's not a problem because later we will have an example. I will show you guys how it works. And after you understand the example, then you go back to this page, you will know what they are saying here. Then the key idea is from time to time, each node will send its own estimated distance vector to neighbors. So when X receives a new estimated distance vector from neighbor, it will update its own distance vector using this BF equation. It's this equation. So under a matter or natural conditions, the estimated capital D y converge to the actual least cost lowercase x y. And for this one is the ground truth. And for this one is our estimated least cost on the path from x to y. So under minor and natural conditions, so finally, these two, this estimated one and this ground truth one, they will be equal to each other. So that's the key idea of a distance vector algorithm. And also, iteratively and asynchronously, each local iteration will caused by this local link cost change and the distance vector update message from neighbors. So when the routers will update its distance vectors, it will based on these two conditions. Either one can trigger the distance vector calculation for the current router. One is a local link cost change. Another one is a distance vector update message received from its neighbor and then distributed. So each node notifies neighbors only when its distance vector gets changed. So that means these two conditions can trigger distance vector update for the current router. However, these two conditions may not update the distance vector for every single time. Sometimes after the calculation, the router will still keep the original or the old distance vector because the new update cannot um, or cannot get a better path or link cost compared with the old one. If that's the case, the current router will not send the distance vector to its neighbors. However, if the current router's distance vector get changed, it will notice its neighbors. Therefore, for each node, it will do this set of things. The first thing is wait for the change in local link cost or the message received from neighbors, which is two conditions. So either one can trigger a recalculation for the distance vector update. Then, suppose there's one condition gets satisfied, it will move to this recompute estimated step. And after that, if the distance vector to any destination has changed, it will notify its neighbors. Then let's see our example. So on the right side, we can see for this topology is quite simple. It just only have three routers, X, Y, and Z. And the link cost from X to Y is equal to 2. From X to Z equal to 7. And from Y to Z is equal to 1. So initially, first let's see node X table. So X will know it will maintain this kind of a table. For this column is the router name, same as this row is the router name. Here, for this column and this row will include all the routers in this topology, and then the distance vector for X itself is the first row. X to X, the distance or the cost, I'm sorry, not distance, the cost is 0. And from X to Y, the direct path we know is cost with 2. From X to Z is equal to 7. However, since the node X didn't get a message from Y or Z yet, therefore the distance vector for Y and Z here will be set as infinity. So the same thing or same action done by node Y and node Z. So after they initialize their self distance vector, and then they will send their distance vector to its direct neighbors. After they send it to each other, so first let's focus on node X. Let's see this table. After node X receive the distance vector from Y and Z, it will do recalculation. So the recalculation is based on the BF equation, which is this one. So first, let's see how the X calculate the estimated least path cost from X to Y. It will check all the possible paths. So first, let's see the cost from X to Y, which is a direct path, is equal to 2. And from Y to Y is equal to 0. Another path is from X to Z, which is equal to 7. And from Z to Y, we get it from here is equal to 1. Therefore, after the calculation, this combination will be equal to 2, and this one equal to 8. So the smaller one is still 2, which is directly from X to Y. Therefore, we will leave 2 here. And then we continually to check the distance from X to Z. And also we will check all the possible paths. So first, let's see from X to Y is equal to 2. And from Y to Z, we know it's 1 is here. And for this result equal to 3. And from X to Z, this one is equal to 7. And from Z to Z equal to 0. So the combination is 7. Then after we do the comparison between these two, we know 3 is smaller. Then we know we do an update for the distance vector of X. We change the distance from X to Z equal to 3 instead of 7 here. And the same thing will be done by node Y and node Z. However, after the calculation, node Z will update its distance vector here. But node Y doesn't get any change, so it will leave as is, like this. Because node X and node Z, they have updated their distance vector, this one and this one. Therefore, they need to notice their neighbors. So node X will send this distance vector to neighbor Y, this link, this path, and then neighbor Z. The same thing for node Z will send update to neighbor X and neighbor Z and neighbor Y. I'm sorry. After this updating, you can see, so everybody get the same distance vector set. Actually, this is the ground truth for this topology. Then let's see the link cost changes. So the node detects local link cost change. Then it will update its routing information and do a recalculation for the distance vector. If the distance vector gets changed, it will notify its neighbors. So for this case, the link cost xy will change it from 4 to 1. Then let's see how it works. So at the time t0, y will detect the link cost change. It will update its distance vector, then informs its neighbors. So at the time t1, Z receives update from Y. Update its table and computes new list cost to X. So for this update, the path cost will change from 5 to 2 because initially the path is Z, Y, X, 1 plus 4 equal to 5. However, currently it still uses the same path, Z, Y, X, but the cost will be changed to 2. Then sends its neighbors its destination distance vector. At the time t2, Y will receive this update. Updates its distance table, and Y's list cost do not change, so Y does not send a message to Z. And also we know because the link cost will change from 4 to 1, which is a good news. Therefore, the travel is quite fast. However, let's see another situation. If the link becomes worse, for this example, the link cost changed from 4 to 60. So node detects local link cost change, and for this time, the bad news will travels slow because it will encounter the count to infinity problems. So Y can cause this count to infinity problems. Let's do a quick calculation. Suppose after the link cost get changed from 4 to 60, router Y will do a update, will do a recalculating. Then let's see this dy and x, which is the minimum of all the combinations. So the cost from y to x plus the estimated path cost, which is x to x. That's the first combination. The second one is from y to z plus the path cost from z to x. And then we know the cost from y to x will change to 60. And x to x is equal to 0. The cost from y to z is 1. And the dzx will be equal to 5, which we can get it from the distance vector of z. After the calculation, we can see this one equal to 60 and this one equal to 6. So the result will be 6. However, because this topology is quite simple, we can directly to see the ground truth. So the distance from y to x, excuse me, is equal to 1 plus 50. Actually, is equal to 51. However, we get a wrong result, which is 6, because it cannot directly get this ground truth based on the local information and also based on the distance vector of its neighbors. So for this kind of wrong bouncing will be continually for 44 iterations before the algorithms stabilized. And also for if you are very interested in how they bounced for 44 iterations, you can check the textbook. And for this part, actually, is on 376 page if you check the textbook. So you will know the details of this count to infinity problems. However, how to address this count to infinity problems? Actually, we have a solution. We call it poisoned reverse. So how this one works? If z routes through y to get to x, then z will tell y is z's distance to x is infinite. Actually, the mechanism of this poison reverse is so when z route to x through y, z just tells y that the dzx is equal to infinity, and y will route to x directly as 60 and update this information to z. Then z will route to x directly as 50 and notice y. Then y will update the distance vector to x through z as 51. Since y route to x via z, so y will tell z that the distance from y to x is equal to infinity. Therefore, after they apply this poison reverse, they can avoid this bouncing for this wrong result, like this the upper example show us. However, here we have a question: will this completely solve the count to infinity problem? But actually, unfortunately, the answer is not, because the looping is more than 3 nodes for most of the case. So you cannot suppose those nodes they are directly connected with each other. Um, the poisoned reverse works because the x, y, and z for this upper example they are directly connected with each other. However, in the real case, the topology of the entire network is more complicated than this one. So the poisoned reverse solution may not always be working for this count to infinity problems.